First, a few words about me. I have been a PyPy co-developer for about 6 years now. Well, it's basically my job to work on open source and or to do consulting related to it. Well, I have a mail and a Twitter, how original. This talk, so before diving into C extensions and how we support them in PyPy, which is what's called CPython, just a quick introduction to PyPy and a few words about what we're doing at the moment, especially because this is, I think, the only PyPy talk at the conference. So, PyPy, that's our elevator pitch. PyPy is a fast, compliant alternative implementation of the Python language. So, what it means, well, first it means that we run Python programs. But more than that, we try to be compliant with, well, the specification of the Python language, which, as you probably know, is just the source code of CPython. So that causes a few issues. But nevertheless, we managed to do that and to provide very decent speed for Python programs. So to have an idea of the architecture of PyPy, I like to start from the architecture of CPython, which is a bit simpler. So, well, CPython is written in C, as you know, and in the Python executable, you have two main parts. You have the compiler that takes the source code, turns it into bytecode, and you have the bytecode interpreter that takes each bytecode and runs a specific operation corresponding to the bytecode. PyPy, it's quite similar, except that, well, in the interpreter, on top of the bytecode interpreter, we have a just-in-time compiler that works by observing hot loops in the code, or, well, any sort of code that runs often. And then this code is traced, analyzed, and so that it gets runtime information on the types, and with this, it emits optimized machine code. Now the magic in PyPy comes mostly from the Python toolchain up there, which generates more or less automatically the just-in-time compiler, and also adds other features that work with the JIT, like the GC. The other good thing about this toolchain is that the language we use is EuroPython, which is a subset of Python, so we can easily test the interpreter. Now, another difference between CPython and PyPy, it's to do with the memory management. So in CPython, it's well, it's just a standard C application, so it uses just malloc and free and all that, which is not ideal for an interpreter that tends to allocate small objects in random places all the time. And also, due to this simplistic model, CPython needs to update reference counts all the time. And in contrast, PyPy has quite a performant garbage collector, which is specially tuned for Python. And that way, and also it works well with the JIT. And there's an observable user difference, which is when, at which time does the allocation happen. In PyPy, since we have a garbage collector, the allocation happens when the object is collected by the garbage collector, whereas in CPython, it's when the reference counts hit 0, which happens because you've told the interpreter to decrement the reference count. So in CPython, you know when the allocation happens, usually, but the most interesting difference between PyPy and CPython, it's speed. So people often say that PyPy provides magic speedups, and it often does, but it can do more than that. It's true that, if you're lucky, you can have your program that used to run on CPython, try PyPy, and cool, it's twice faster. That sounds great, but actually, if you, in such a case, if you try to optimize for PyPy, you could get your code to be 4 times faster than on CPython. So why stop at just running PyPy? If you want to reap the benefits, optimize. And, as usual, if you want to optimize, you first need to have good benchmarks. And a good benchmark is something you really care about. So it's not a micro benchmark, it's not a test, it's something that matches the way you really use your code. And once you have a benchmark, you should use a profiler to find the hot parts of the code. And on PyPy, there's basically only one profiler that understands PyPy. It's called vmprof. And once you've done that, then you can actually modify the code and a few pointers for doing that. First, you need to avoid dynamic features at runtimes, or at least in inner loops. So it's fine to use metaprogramming as much as you want before you run your main computation, but in the inner loop, there should be none of that. A side benefit of having a JIT is that you can use function calls because function calls are usually inlined by the JIT. So so you're free to structure your code, and there are a few optimizations that you need to be aware of in order to hit them and or to avoid disabling them by accident. So the one is that attribute access on instances is well optimized. Effectively, it's as if every class had a slots declaration, and you don't need to look up an attribute name in a dict. And the other thing is that we have what we call list strategies. So when you have a list that contains a homogeneous list containing built-in types like ints or floats, then access will be very fast. It's as if you're indexing a C array. Let's have a few words about the current status. I'll start by Python 3. So we had our first fully supported release of of any PyPy 3 last Christmas. The latest version was released in April. So what we support is 3.5 at the moment. And it's, there are still things missing on Windows, but it's fully supported on Linux, Mac, BSD. And what we're working on, it's 3.6. We are about halfway, which is always a hard thing to say, but I hope there's not that much left. At least the main syntax features are there. Now it's only the details. And for Python 3, we need to work on more optimizations for things that, for things that didn't exist in Python 2, like the fact that we have Unicode everywhere. Async stuff is, we need to find ways to make it a bit better. It's decent, but it could be better. That's it for Python 3. Python 2 had a release at the same time as the Python 3. In this release, apart from the, in this release, we mainly had a few incremental improvements. So, I'll remind you that cffi is still the best way to talk to C code, and it keeps being updated with every release of PyPy. But the main highlight of the last release was the improvements to C extension compatibility and speed. And so now you can pip install the main scientific libraries. And we have a few wheels that you can check because they are not, you have no PyPy wheels on PyPI because of issues with many Linux. And so if you use PyPy, check out this website and you'll get binary wheels. So with this, I start the main part of the talk, which is CPyExt. So CPyExt, what is CPyExt really? As a user, you could just think of it as python.h for PyPy. When you want to, when you need to compile a C extension, you link it against, you compile it against python.h. You do that on CPython, and on PyPy you do exactly the same. With this python.h, the compiler will know where to find the actual C function you want to call from the extension. So what's in CPyExt? Well, this python.h is mostly generated during the PyPy build, and we have a bit of C code that, sort of handwritten C code, which is mostly a copy from CPython, but most of the implementation comes from our Python implementation. And, well, what does it look like? Looks like this. So this is our Python code. This is the code that implements PyList set item. And if you've already looked at the CPython source, you'll notice that it's mostly the same logic. Well, we have some error checking, and then we find where the well, we fetch the place where we store some item in the list, and we update, and we do a decref because the old object is not referenced anymore. So this is, well, this looks quite simple, and this is the good thing is that it is debuggable and testable because it is using our Python. However, this hides a lot of complexity, which is in this decorator at the top. And this decorator at the top does all the magic of moving between the C world and the RPython world. And there's quite a lot of thing to do, like all that and that. And so what do we need to do to make CPyX work? So we have two very different worlds. When we have a C extension that tries to talk to the PyPy interpreter, so the implementation languages are different, but this means that the internal object structures are different. We have completely different memory model inside PyPy. We have managed memory. We have a garbage collector that can move the objects around, and but that's quite incompatible with the C model, where you refer to things using pointers, and pointers are basically locations in memory. So if things move around, C code gets confused. And in PyPy, we have also, well, a lot more control on what's going on. We have exceptions that can propagate, and so we have internal exceptions inside the interpreter that are used, for instance, to implement the user-level exceptions. And but on inside the C extension, there's well, there are no exceptions in C, so extensions need to set a thing called an error indicator that the interpreter needs to check from time to time. Also, C extensions need to deal with ref counts because you, well, you need to know when an object can be deallocated. And but inside PyPy, we have a garbage collector, so we don't worry about that at all. And so how do we bridge this? And the main idea is to have these C objects linked to Python objects, so they so that they are basically just proxies for the actual object. And the specific mechanism is just this line here. So if you know CPython, you'll notice that this PyPy link is the only difference with what CPython does. And this PyPy link allows allows the CPyX layer to query the memory manager in order to find the PyPy object. And well, and then it's just a matter of, well, it's a small matter of programming to implement all the C semantics. So you need to remember your increfs and decrefs when you are implementing API functions in Python. But there are more problems, like what do you do when if you want to call a C function from Python, which is the whole point of having a C extension, and so that's why we have these magic decorators that handle the transformation magically, and basically, yeah, we had levels of indirection. Anytime we need to cross a boundary, anytime there's something to check, because we are back from the C world where anything can happen. So that's the general idea. But well, you probably know the rest of this quote, or actually folk saying, which is that all problems in computer science can be solved by another level of indirection, except the problem of too many layers of indirection. And we've recently noticed that we had too many layers of indirection. So this was last year in Cape Town. And we've started to improve the performance of CPython. So, as I said, crossing this boundary is it's expensive, and because we have this magic going on, we do it even without realizing, because we don't need to explicitly convert between the C world and the PyPy world. It happens behind the scenes. So we need to be more careful about that. And by being more careful, we can remove a lot of this back and forth, because it's in many cases it turned out to be completely useless. And well, it's an extension of this idea, which is when you have an operation that can happen completely on the C side, then we should just implement it in C and never cross the boundary. So, well, this requires some care as well, because because of the different underlying assumptions of PyPy and of the C world, but it's possible, and well, we've started doing it. It's not complete, but the results are here. So in blue, it's just CPython as a reference. Green is PyPy before these optimizations, and red is after. And this is a bunch of rather silly micro benchmark, so that we just check the well, the overhead of each specific operation. So we used to be between 4 and 6 times slower than CPython, and now we are between the same speed and 50% faster. So there's hope for the speed of CPython, and the future, well, it's to continue working on this. We can, so there were a few red bars that where we were still a lot slower than CPython. It's probably doable to be faster than CPython in all cases. It just requires work. And well, we have PyPy open space this afternoon at 2. So if you want to come discuss with your own PyPy problems or your ideas. And well, that's it. I'm waiting for your questions.
Anyone questions?
Were there any C extensions that this PyExt was written in mind for, or is it just for the general case? And does that make sense?
No, it's for the general case. Well, there are extensions we've been using as test, and also because they are extensions we would really like to make compatible with PyPy. And well, it was mainly NumPy, and it's now it fully supports PyPy now, I think.
Can you say which rule?
No, because I don't know. Sorry? Harris 1.
When will PyPy drop support for Python 2?
The current official answer is never. We'll
Any reasons for that?
Well, a lot of our users are still on Python 2. And our toolchain is implemented in Python 2, so that's another motivation. And also, as language implementers, we are quite happy to have something that doesn't change. And so, well, these are all the reasons why PyPy likes Python 2. Well, we see no real reason to drop Python 2. We have two branches for Python 2 and Python 3 that share a lot of code. So it's not a major burden to keep supporting Python 2 either.
I have a question about EuroPython.
Yes.
How is it related to CPython? Is it a subset or something like that?
Well, it is a subset. You can run our Python code as Python code, and that's what we do a lot for testing, and that's quite convenient. But the exact definition of our Python is just the subset of Python that can be understood by the toolchain.
So what about Cython? Does this extension compatibility layer make us make PyPy compatible with Cython?
Yes. Cython is fully, well, I won't say fully because there's one piece of code in Cython that's CPython specific, but apart from that, Cython is fully supported, and extensions that use Cython now work on PyPy. Scikit-learn, which uses a lot of Cython, now has experimental support for PyPy, for instance. And LXML has supported PyPy for years.
Thank you very much.